So, welcome everyone to Lecture 8, Deep Learning for Natural Language Processing, Summer Semester 2020. We're talking today about recurrent neural networks. So, in the previous lectures, we started out with multi-layer perceptrons, and then we saw all of the details of those, like what we're doing in deep learning. We minimize the loss function. We choose a batch size for the learning process. We have different activation functions, etc. So we saw all of the material for a basic neural network. Then in the next lectures we talked about embeddings, which are continuous representations of different things. They could be words, letters, sentences, or whole documents, and these representations is usually what we use at the beginning as the input of our neural networks. So in this lecture we will talk about a very important extension of the multilayer perceptron, which are so-called recurrent neural networks. You have already seen the basic principles, but we will discuss them again today. Then we see further extensions. For example, we make them bidirectional, and we make also dependency relations between the output units. Then we see how we use them in sequence tagging and sentence classification tasks. And then we check several NLP applications where recurrent neural networks are the method of choices, at least until recently, let's say at least until 2018. And one of those applications is, for example, language modeling, which you have also seen already in previous lectures. And then finally, in the second part of today's lecture, we will talk about one of the big problems of basic recurrent neural networks, and these are so-called vanishing gradients and also exploding gradients, and we will see simple remedies. And then finally we will talk about gated recurrent units and long short-term memory networks that are special cases of RNNs that can address vanishing gradients. Good, let's go into the basic principles. So remember, feed-forward networks, also known as multi-layer perceptron. You have the input that's coming into your network. You feed that forward through the network through several linear activation functions combined with non-linearities, and then you get your output. We can write this in different format, that we say the input is at the bottom, then we have a hidden layers which come in the middle, and then the output layers which come at the top, and they are connected by matrices. If we go to the recurrent neural network, the extension is that we have a recurrent connection that connects the hidden state with itself, with the previous hidden state. And of course, for recurrent neural networks, we have this time index where the inputs come at different time steps. And of course, there's a time delay for the hidden state, so it cannot immediately feed upon itself, but you have to make the current hidden state a function of the previous hidden state. And then the hidden state is also what we would call our memory. That's where we can store information about the current, about the presence, but we can also store information about the past via this recurrent connection. And we have matrices that connect the initial layer, the input layer, with the hidden layer. This matrix we call U. Then we have a matrix that connects the hidden layer with the output layer. That matrix we call V. And we have a matrix that connects the hidden state with itself. We call that W. So how does it look formally? The input vectors, there's an unlimited number of input vectors, so to speak. They all have dimensionality n, and we, for the sake of getting the math correctly, we perceive of them as row vectors, but you could also perceive of them as column vectors, and you just have to switch the order of the inputs and of the vectors and the matrices that you multiply. So these are given, so they come in from our problem definition, so to speak, or maybe we use word embeddings. Usually we use word embeddings for them. Then We have the hidden state. The hidden state is given, we multiply xt times the initial matrix U, we add to that the previous hidden state multiplied by W, and we add our bias values to that, and then on top of this matrix product, or this vector addition here, we put a nonlinearity, and we will apply this element-wise unless the nonlinearity is softmax. And then here's the dimensionalities of these vectors, so you have to check that everything is fitting. The U matrix has to map from R to the N to R to the D, because the input lies in R to the N. And D is some hidden dimensionality that you choose, right? You can choose your hidden dimensionality to be small or big, and this may of course affect the performance. If you make it too small, then your model is not able to fully model the problem that you have. If you make it too big, you may have problems of overfitting. So that's a number to choose very carefully. Then W is a D times D matrix. That is because the hidden dimensionality is D, and we take a vector of size D, and then we map it to a vector of size D. And then finally the output. Well, okay, so here's the output. The output is given by taking the hidden state vector, multiplying it by V, and adding again bias values, and then V has that, and then we, on top of that, we apply a nonlinearity, sigma Y, that would in NLP would typically be the softmax function, because often we want to do classification, so we want to choose one element from a list of other elements, and that's modeled well by taking the output to be a probability distribution. Then we can take the most likely element, or we can sample from that probability distribution. And therefore this V matrix has size D times N, where D is again given by the hidden dimensionality, and M is just in NLP that would be the number of classes that we have. Like if we do a 10-way classification, then M would be 10. What we optimize is, we want to optimize the average loss over the individual time losses, ET. So we have a loss for each time step, and then we average that to have an overall loss. And the loss for each time step in NLP, that would typically be the cross entropy between those two distributions. YT is the prediction of our model. And then this TT here is a little bit a strange looking notation. This would typically be a one-hot vector in NLP, which says I pick class number 3, for example. So the truth at times T could be a one-hot vector that has a 1 at index 3, for example. And the cross entropy loss, you know how that is defined. It looks like this. It's a sum of the indices of the components of T multiplied by the logarithm of the components of Y. And if TT is a one-hot vector, then only one component will survive here, and all of the others will be 0, right? And then, as I said, we average over all of these ETs. So we have the individual T for each time step. We average over all of them to get the complete loss. Now we make an example. So the example is a rusty can. Let's assume we have word embeddings that we obtained from somewhere, and these embeddings look like this. They are three-dimensional. 3 is an arbitrary size that I chose for, not arbitrary, it's a small size that I chose for illustration purposes. But in reality, that would be like 100 or 500 or something like this, right? So let's assume these embeddings are given by these vectors here. Let's say the truth for this input is A is a determiner, rusty is an adjective, can is a noun. And this truth will be encoded as one-hot vectors in a 4D label space. What do we mean by this? 4D label space means we have 4 labels overall. So Let's say we only have these three plus one additional label that we can possibly use to label our data. Maybe the fourth label is verb, right? So we have a 40 label space, so the so the truth vectors will be 4-dimensional, and they will be one hot. They will have one exactly for the index of the current label. And let's say we use relu activation for the hidden layer and softmax for the output layer. This is a very plausible solution that we would choose in reality also. Let's say we get our initial matrices U, W, and V as follows. So we said U is that maps the input to the hidden layer. So the hidden state we choose as being of size 2. In this case, we arbitrarily set them to be of size 2. We choose one matrix randomly. In this case, it has this form. U then maps from the input to the hidden space, so it should be 3 times 2-dimensional. That's also a random choice here. And then V maps from the hidden state, which is 2-dimensional, to the output space, which is 4-dimensional, right? And we choose that matrix here. Our bias values, we choose them to be 0 vectors. And the initial hidden state, so that's also important. We need to have an initial hidden state for recurrence to work. We choose that to be the 0 vector also. So let's look at the example. We feed in. We have our input, a rusty can. We map that to word embeddings. Then once we have our matrices, we can compute the initial hidden state. And how does that look? We multiply x1, which is this here, times u. U was given in the previous slide. It's here. We add to that h0 multiplied by w. H0 is 0, so that cancels. B also cancels. So we just do this vector matrix multiplication. We apply relu on top of that. And if you do the calculation, you can convince yourself that 1, 1 is coming out. Good. Then in order to compute the second step, we need to have the input here. And we also need to have the input of the previous second step. And this is also a reason why parallelization is not possible with recurrent neural networks, because you always have to wait for the previous hidden state. So if we do the calculation, we get x2 multiplied by u plus h1. H1 is this one here times w plus b, which is 0. Relu applied on that, and that becomes 5, 4 if you do the math. Analogously, we can compute the third hidden representation. Once we have the hidden representations, we can compute the output representation at each time step. So the output vector at each time step, that is given by ht times w plus c, and then we apply the softmax function. And then, as you can see, that really gives a probability distribution. If you add up the numbers, you can see that these are probability distribution. Here, for example, it's 96%, plus 2 is 98, 99. And then there's rounding errors, right? So if we would do the exact numbers, that would be 1. And the same here and the same here, right? Then let's say our truth vectors are those one hot vectors. That means the first vector is the index. So this is the index of the first label in our label space. This is the index of the second label in our label space, and this is the index of our fourth label in the index space. And it's absolutely arbitrary that this is 1, 2, 4. It could be any other. Values depending on how you index your label space, and depending on the actual labels, of course, that you have for those words. Then we compute the loss. This here is 1 times log 37, and then we take the negative of that, so we get that loss. We get this corresponding loss here. We get the corresponding loss here. So this is minus infinity. You can see here we get a very big loss, because we should predict this label here, but we reserve no probability for this label. So we get a very, very large loss here. And then the total losses, we just sum that up. So that is the forward pass. Now we can compute the gradients and update the weights to change our weights. To change our three matrices. The three matrices are U, W, and V. So we would do the backward pass to get the gradients, and then we change our matrices. And that would be similar to the multi-layer perceptron case that we have seen previously. So how do we do? Just a few more words on the weight update. So we compute the gradient similarly as in standard multi-layer perceptrons, but we need to keep in mind here that several parameters are shared. So we have several shared parameters. They are given by different colors here. So the U is shared over all time step. This matrix here is shared, and the matrix corresponding to that arrow is also shared. So we have to keep that in mind. And we need to do a few modifications, but they're really not too difficult overall. Some people call backprop for RNNs as backpropagation through time, and we're not going through that, because TensorFlow and Keras and all of these libraries, that's what they are there for. They do this for you, right? So we don't have to do that ourselves anymore. And if you want to do it brute force, you can of course also do it numerically, where we already said. So if you have a small individual weight, then you take the current weight matrices, and at the position of this individual weight you add an h, and all of the others you leave unchanged, and you subtract the 2, divide by h. So this is a numerical approximation of the derivative, and f is the loss function, of course. So we want to minimize our loss, and you could do this also numerically, but this is inefficient, as we already discussed for the MLP case. But it's a sanity check, right? And then we do again the same weight update after the gradient computation, because we do gradient descent. We take our current weights. So this is all. So W here stands for all the weight matrices, right? We have 3 weight matrices plus the biases. So we take those, we subtract minus alpha times the gradient of our loss function to get our new weight matrices, okay? So what are RNN properties? So first of all, they have infinite window size from the left, so we can see all of the parts. We are not limited to the previous 2, 3, 4, or 5 time steps, but we can really see everything that occurred in the past from the left side. So at least in principle. So that's good. But we also want to base our decision on future words or tokens if available. So that's not always available. For example, if you have speech that's coming in real time, you only see the past. You don't see the future. But for other problems, when a sentence is given and you want to classify one token in the sentence, one word in the sentence, you can, and it's written text, you can see the previous text, and you can also see the future text, right? So in many other cases, both past and future are given. So that leads to bidirectional RNN. So you run a second RNN from right to left. With independent weights, you concatenate a forward and backward hidden state. So you have 2 hidden states at each time step. You concatenate them to have one big hidden state vector. And then V becomes of dimension 2D. So if they each have dimensionality D, then that would become 2D times M.